This video will show you how computers work, and we will build one from the ground up. My name is Adi. I'm a software engineer at Amazon, and I've been on 3 teams so far, from pure backend stuff like catalog administration to ad tech, and now in R&D. I also studied computer engineering at UIUC, and what I found helped me in software engineering has been a deep understanding of hardware. For example, have you wondered about how Spotify works? Like, how does your software all of a sudden feed you music, render everything? Like you open up Spotify and it pulls all your playlists from a database. It renders your album art on your screen. It streams your music to your headphones all at the same time. In this video, we're going to try to clear everything up. Most of these parts used to be really intimidating, like the CPU, RAM, GPU. But once I had a deep understanding of them, I was able to really understand how to write good software and how exactly everything worked. And it really just starts with a simple idea of a switch. No, not that switch, but this switch, a light switch. Imagine you have a flashlight. It can either be on or off, and that's it, two states. Computers use this exact principle with electricity. So state one is torch off, state two is torch on, and you're either sending electricity through or not. And that can be represented as a 0, which is off, or 1, which is on. And this is called binary. You might have seen this across like TV shows or like just like generally what you think is happening in a computer. And it's true. It's just ones and zeros telling like the computer like what to do. That's every photo, every line of code translated into ones and zeros, every song. It actually like sound waves are turned through Fourier transforms, but that's not relevant here. At its core, it's just a massive, massive sequence of these ones and zeros. But just storing ones and zeros isn't enough. A computer needs to think. To do that, we combine these simple on and off switches into something called a logic gate. A logic gate is like a tiny decision maker. For example, a simple AND gate will only output 1 or on if its first input and its second input are both 1. So if you have two flashlights and they're both on, then the third flashlight would inherently be on. And if I saw the third flashlight, I don't even need to see the first two flashlights because I know the third flashlight can only be on if the first two were on. And when you combine millions or even billions of these tiny gates, you have a machine that can do math. This used to be really intimidating. This used to be in all my college textbooks, and admittedly so, like this made me actually stay away from learning hardware, but it's actually quite simple. And this is what you actually see in the real world. But like in its microscopic state, that's what it looks like. And so the CPU, that like this is like something you can build actually by hand too. It's just like the brain of a computer. It's a chip packed with billions of these logic gates called transistors, one of the best inventions ever created, and all wired together to perform calculations. And inside a modern CPU, you'll also find like several cores, which are basically several smaller CPUs as part of the larger CPU. And a good way to think about it is, say you have a big program to run, like a video game. It's like a massive project, and we'll call that project a process. And the process has many different tasks that need to be done, often at the exact same time, like handling player input or rendering graphics or playing sounds and managing the game's physics. These individual tasks are called threads, and each core in the CPU is like a dedicated hyper-fast worker that can focus on one thread at a time. If you have a single core CPU, that one worker has to be incredibly fast at switching between all these different threads. For example, here, everyone is sharing one one core, and they have to switch quickly in between each other so that it seems like everyone's drinking Coke at the same time. If you watch like Flash, you might have seen like he like zooms past like two locations and it looks like two flashes exist. And it works on the same like actual thread for a few milliseconds and then switches to the other thread. So going back to our game reference, physics thread will be given like a millisecond, and then the sound thread will be given a millisecond, and then the graphics thread, and then back again, and it'll seem like all of it's happening at the same time because our brains can literally not clock that much information that quick. And it does this so fast it creates an illusion, right? And it makes it seem like it's happening in parallel, even though it's not. And if you have a multi-core CPU, say with 8 cores, you're going to have like 8 workers. Now, the CPU only understands one language, though, the ones and zeros. And so what you end up having is programmers writing in code in high languages like Python or JavaScript, and then a special program called a compiler or an interpreter that does things either at compile time or runtime, which we'll go in later, like for a different video, translates it down to more basic human readable language called assembly, which is like how people used to code long ago, where they would literally code into the actual physical or like machine And then eventually that turns into binary machine code, which is like the OG way of coding. Like von Neumann might have coded that way, which was like the guy who came up with the idea of like states and a lot of the computer architecture. And eventually this is what the CPU actually can execute. So we have a massive brain, and the brain needs a place to work, and it needs a desk, right? That desk is your RAM, or random access memory. When you double click an application, your computer loads that program and all its necessary data into the RAM. The RAM is like pretty fast, like compared to an SSD, it's incredibly fast, allowing the CPU to grab that information it needs almost instantly. And the more RAM you have, the bigger your disk is, the more applications you can run smoothly at the same time without your computer feeling slow. Like you might have pulled up Task Manager and like had to force quit some applications because all of them are trying to like push themselves into RAM, which is a limited desk space. Imagine you're studying for 12 subjects and you have all your binders open on your desk. Not only will you not be able to study for anything, but like you'll miss information, and not every like piece of like text will be available to you. Not every textbook could be up on the desk. Like some things will have to be layered. So that's why you put like some of your textbooks into a bookshelf or your backpack, and you only leave the textbook that you need to read in that moment on your desk. But the RAM has one crucial characteristic. It's volatile. This means that as soon as you turn off your computer, everything in the RAM disappears. You have to remember that hardware at the end of the day literally is just holding zeros and ones, which are just electric states. Like it literally has electricity in there or doesn't have electricity in there. That's the 0 or the 1. And if you turn it off, like there'll be a last surge of electricity, and all those states, all those literal hardware pieces holding electricity will just be like randomized, and all of a sudden your data will disappear. So you need to be able to turn off your computer and still be able to hold that, without having your desk wiped clean. So if RAM is temporary, where do your files, your operating system, your games live? That's the job of a non-volatile storage. And examples are like floppy disks, like DVDs, CDs, and hard drives. And even these, like if you don't use them for decades, they'll also like go corrupt and like lose the electric state, because like electricity will literally just siphon out. There's like two main types: hard drive, and an which is called an HDD. And a hard drive is a device with like spinning disks. It literally has disks. It has like this arm that goes up and down. It like reads through the tracks, and it'll literally read it's not etched in, but kind of etched in data. And it'll like move up and down. So there'll be like 10 disks, and like the disks on the top will hold some data, on the bottom end will hold some data, and this robot arm will go up and down and like read the information here or read the information here. And it has a lot of moving parts, so it's like pretty slow. Like you literally have a robot looking for information for you. And then we have something like an SSD, which has no moving parts. It's in itself its own circuit. It uses something called flash memory, like a giant USB stick, to store data. And because there's no physical movement, like you don't have to worry about an arm going up and down, and like there's less things to break actually. It's far faster than hard drive. So we have the brain, which is the CPU, the desk, the RAM, and the library, the bookshelf that's holding long-term stuff like storage or hard drives. But even getting up from the desk, like, I'm gonna be honest, like, I'm lazy. I don't like doing it. And it's slow. Like, you have to move things around, and it can just be like, you can miss things in the process. Like, you can drop a book and forget about it. So, for like the most used information, the CPU has an even faster, smaller memory right on the chip itself, called a CPU cache. You can think of it like a sticky note you put on your display. So L1 cache is the smallest and the fastest. It's for data the CPU needs like right now. L2 is a bit bigger and slower, and L3 is larger and still often shared across all the cores. Think about like a bigger and bigger sticky like note, and eventually you're just like, look, I need a sheet of paper. I'm going to throw that on the RAM instead. And the CPU will always check the cache first. If it can't find the information it needs in the cache, it'll search the RAM. If it can't find it in the RAM, it'll search the hard drive or the SSD. And so it's going to try to be as fast as possible. And there's a lot of scheduling and different like algorithms that are used here to make sure that like the most relevant information is kept in the cache, then the RAM, then the hard drive. So how do all these separate parts, the CPU, the RAM, and storage, talk to each other? Well, they're plugged into one giant circuit board, the motherboard. And the motherboard is like the backbone of the nervous system that connects everything. The intricate lines you actually see on that green board are like copper traces, copper wires. The green board is actually called a PCB, but all you really need to know is this green board can hold all your parts that we see on the right-hand side. The copper traces are literally copper wires that are moving the electricity around. And the goal here is just to move your data, like in something like called an information like highway. Like these are buses that like they literally move information from one place to another, and they do it in the way that like the least amount of electricity is just lost. And so we've covered now the thing that holds all your pieces together, the CPU, the RAM, and honestly, this makes up most computers. Most computers were like this for decades. But then there's like specialized components that really matter, like a GPU. You might have heard a lot about this because like Jensen Huang has become a multi-billionaire. Like his company has gone from a few hundred billion to a few trillion dollars in just a couple of years, and that's because they didn't invent this, but they built some of the greatest tech out there. So a good analogy is like a CPU is like is like a generalist. It's designed to do a jack of all trades. It can handle like really complex tasks or very like simple tasks as well, and very quickly. Whereas a GPU is, it can't do one complex task all at once. It has to do like a bunch of small tasks at the same time. So instead of having, four really strong cores, it has thousands of weaker cores. A good way to think about it is, let's say you have a PhD, that's like a great artist, like incredible artist. Well, you could give him 1,000 crayons to make a masterpiece, or you could give 1,000, middle schoolers one crayon and tell them just color in this portion. And well, who will end up like having the masterpiece done at the end of the day? Well, the 1,000 middle schoolers. And like, that's exactly how a GPU works. It like gives like people that are less skilled, like middle schoolers, just a singular task. Like this area, just put like a little bit of color here. Whereas an incredible artist is going to be making it sequentially. They'll like be doing it much slower, but they can do it alone. This is called parallel processing, and it's like perfect for graphics where you just need a pixel to show up, but like in 10,000 pixels or 4,000 pixels. And it's used to, render graphics, and it's just incredible in a lot of areas. And now it's used for AI modeling or AI training as well, and inference. But managing all this hardware, you don't want to give that access to just any bit of software. You want to be able to give that access only to people you trust, that have like great quality software. And then also, if you were writing your own, you don't want to have to worry about all this hardware. You're only learning this right now because I think it's like relevant, but reality is you'll never really interact with hardware directly. You'll actually interact with operating systems. So you probably have heard or Android or iOS based on which phone you have, or Windows and Mac. If you're a student, you've probably interacted with Chrome OS, which is like pretty bad. And then if you like really hate yourself, you're going to be working with like Linux, Unix, and BSD. But the operating system is the boss. It's the like master software that coordinates all the hardware. It tells like the scheduler like which threads to run, like what I was telling you earlier about switching threads, about like making it seem like all the software is working at once, whereas it's actually just sharing the same calculator across really quickly. It also translates your mouse clicks into commands. The CPU understands, and it gives you some network security. It like handles your file management and your storage, and it does this without like giving too much security or permissions to any software, so it could like break your hardware all of a sudden. And it's really, really like strong because like Windows and Apple are making it, and like how often do they really come up with an update for an operating system? Very rarely. And it's usually the best software engineers in the world working on this stuff. And so going back to our original idea of Spotify, we're going to be covering like basically all these 7 layers of abstraction for computing. So you click on Spotify and the operating system detects that click from your mouse. It then sends a command through to your CPU that basically goes like, okay, we have to open up Spotify. So it starts searching your storage device to find the Spotify application files. Then it moves that from the SSD to the RAM. Then the OS tells the CPU that it needs to start listening to you, and it needs to like follow the instructions, and it has to work with the GPU to display Spotify on your screen. And then you like fetch for a playlist, or you pause a song, and it actively starts like executing those instructions, and working with something called a server or client. You're the client, and it works with the server to like handle requests. And I'll be going into a video of like networking and how these requests work as well, later. And then essentially you're eventually having that song sent to your sound card, and you're able to listen to your music at any point you want. And so The components of this like computer architecture really boil down to like how are you doing your calculations? How are you storing everything? How are you working with your input devices, which are like keyboards and mouse, and output devices like displays? Um, and it really, you don't have to worry too much after that because the operating system actually handles the rest of it. So I hope you guys enjoyed. This really helped me understand like how to do good software engineering. Of course, you can dive much deeper into any of the hardware pieces. So if you want like actually deep dives on any of these, feel free to let me know. But I think if you're just starting off in software or like computer science, this level of abstraction is like good enough. It's probably going to save you 5 years of your life from like computer engineering, like studying. So yeah, hope you guys enjoyed.